A century ago, Albert Einstein reimagined the universe not as empty space, but as a flexible fabric he called space-time. In his theory of general relativity, he proposed that massive objects warp this fabric, creating gravity. But Einstein went further. He predicted that when massive objects like black holes or neutron stars collide, they send ripples, gravitational waves, through space-time. These waves, he said, would travel at the speed of light, carrying the story of their violent origins. Einstein doubted we'd ever detect them. By the time they reached Earth, the effect would be unimaginably tiny. For decades, gravitational waves remained a beautiful theory, undetectable, a ghost in the cosmic machine. But the idea was too compelling to ignore. If we could listen to these waves, we'd unlock a new way to observe the universe. The prediction of gravitational waves was a promise, a new sense with which to explore the cosmos. The search began in the 1960s with Joseph Weber, who built massive aluminum bars hoping to catch the faint ring of a passing gravitational wave. His early claims of detection sparked excitement, but couldn't be replicated. Earth's constant noise drowned out any cosmic signal. The challenge was immense, measuring a change smaller than a proton, amid seismic and electrical noise. For years, the universe remained silent, and the technology lagged behind the dream. But scientists persisted, refining their methods and moving from resonant bars to a new idea: laser interferometry. This technique split a laser beam down two long tunnels. A passing gravitational wave would stretch one arm and squeeze the other, creating a measurable shift. It was like trying to hear a pin drop in a hurricane, but the potential was enormous. This innovation planted the seed for LIGO, the Laser Interferometer Gravitational Wave Observatory. The dream of hearing the universe was alive, waiting for the right instrument. After decades of work, LIGO was ready. Two giant L-shaped detectors, each with 4-kilometer arms, built to sense distortions smaller than an atom's nucleus. For years, they listened in silence. Then, on September 14, 2015, a signal arrived, a clear, rising chirp, first in Louisiana, then in Washington. It matched Einstein's predictions. Two black holes, each about 30 times the mass of the Sun, spiraling together and merging. In a fraction of a second, 3 solar masses worth of energy was released as gravitational waves. Humanity had, for the first time, directly detected a ripple in space-time. This was a scientific revolution, opening a new window onto the universe. Since then, LIGO and its European partner Virgo have detected dozens more events, including neutron star collisions. Gravitational wave astronomy was no longer a dream, it was real, and it was just beginning. We were no longer just looking at the cosmos, we were listening to it. LIGO's success inspired even bigger dreams. To hear the universe's deepest rumbles, we need to go to space. Enter LISA, the Laser Interferometer Space Antenna. LISA will be a triangle of spacecraft, millions of kilometers apart, orbiting the Sun and beaming lasers between them. It will detect low-frequency gravitational waves from supermassive black holes, and possibly even echoes from the Big Bang. LISA will reveal cosmic events invisible to traditional telescopes, mapping the dark universe. With LIGO on the ground and LISA in space, we're assembling a full orchestra of cosmic sound. Each new detection brings us closer to understanding how the universe works and where it's headed. We are at the dawn of a new era, listening to the songs of space-time itself.